In this video, I want to spend a little bit of time to talk about Young's modulus and how to calculate it. Okay, what's Young's modulus is. And Young's modulus is really a measure of the stiffness of a solid material. Okay, that's a stiff. It just measures the stiffness of a solid material, and it's usually given by the idea of Young's modulus is usually given by stress over strain. Okay, and how we represent this is the idea that the stress is going to be equal to the force of tension, okay, divided by A, and we're going to explain what that means. And then the strain is given by L divided by delta L. Okay. So the strain is given by L divided, well, actually delta L. So it's delta L divided by L. I'm sorry about that. So the strain is given by delta L divided by L. Now let's explain what these means. Okay. Well, the force of tension, that's just a tension force. Okay. A is the cross-sectional area. So the cross-sectional area. Okay. And in some cases you'll have to use the idea of a pi r squared to find the cross-sectional area. Okay. Now L is the original length. Yes, so the original length. L is the original length. Okay. L is the original length. And then delta L is the stretch of the wire. Stretch of the wire. In most cases, we're talking about solid materials. We usually talk about wires. So that's the idea. So putting this all together, the Young's modulus is equal to stress over strain, which is just the force of tension divided by cross-sectional area, all divided by delta L over L. All right. And we could simplify this more by actually just multiplying by the reciprocal on the bottom. So the Young's modulus is really given by the force of tension over the cross-sectional area multiplied by, when we flip the bottom, this becomes L over delta L. Okay, and this is how we actually calculate our Young's modulus. Okay, so this is the formula. Okay, now I want to talk about how Young's modulus is related to the interatomic bond. Yeah, so the Young's modulus is actually equal to the stiffness of an interatomic bond divided by D. Now, what is D? What is D? D is the average bond length between the atoms. Okay, the average bond length between the atoms in the alloy. Okay, or in the material. So that's what D means. The average bond length in the alloy. In this case, it could be a rod. Okay, so let's talk about how to calculate this bad boy. So I have this problem here, and it says a wire is made of an unknown alloy, hangs from a support in the ceiling. You measure the relaxed length to be 1.2 meter long, and the radius of the wire to be 0.0031 meters. When you hang a wire, I can't read what I write, but when you hang a 4 kilogram mass from the wire, you measure that it stretches a distance of 5 times 10 to the negative 3 meters. Okay, the average bond length between the atom is 2.5 times 10 to the negative 10 meters for this alloy. So if you treat the wire as a macroscopic spring, what is the overall spring stiffness? Well, remember how we relate the spring force to the stiffness. We say the spring force, or the magnitude of the spring force, is actually equal to K sub S, where K sub S is the stiffness times delta L. So if you want to find the overall spring stiffness, well, K sub S is going to be equal to the spring force. Yeah. This is a vector, guys. The spring force, magnitude of the spring force divided by delta L. Well, we know delta L. Delta L is the remember we defined delta L as the stretch of the wire. So we said that you measure that it stretches a distance of 5 times 10 to the negative 3 meters. So we know what delta L is. Now, what's the spring force? What's the spring force? Okay, Well, usually when we talk about the spring force, we talk about the idea of gravity. Okay, so you could imagine that we have a ceiling here, and we have the alloy here, and this is the, let's say this is the wire, and you hang a 4 kilogram mass from it. So this is some sort of mass. Okay, at this point, the only thing that's the only forces that are on my mass, yeah, the only forces that are on my mass that are actually canceling out the spring force is gravity. Yeah, I have gravity that's pulling down, so this is F of grav. Okay, so that means the first spring force has to be equal and opposite. Okay, the spring force has to be equal and opposite. Okay, and because you could imagine it's hanging from the ceiling. It's hanging from the ceiling, which means that it's static. It's static. Okay, it's a static problem. So that means the spring force going opposite of gravity, you want to push the wire back up, and gravity is pulling the mass down. Okay, so the spring force is pulling the mass up, going back up to the ceiling, but gravity is pulling it down, and that's why the block is static. And so the spring force has to be equal to the gravitational force. So we know this to be true, and we know the gravitational force. So in other words, my spring stiffness is equal to mg 0, 1, 0 as a vector divided by delta L. Okay. Now we know this is only in the y direction, so we don't, at this point, we're not going to rewrite this as a vector. So we know the mass is 4 times the gravitational force of 4 kilograms times 9.8 meters per second squared. Okay. So we multiply these two, mg, okay, and we divide that by 5 times 10 to the negative 3 meters. Okay, so in this case, when I plug that all in my calculator, 4 times 9.8, that's 32.9, and I divide that by 5 times 10 to the negative 3, yeah, I shall get what, 7840 Newton meters. Yeah, so this will be my answer. Okay, so that will be my answer for the overall spring stiffness. Now, what is the value of the Young's modulus for this alloy? Well, we just talked about it. We just said the Young's modulus is equal to the force of tension divided by the cross-sectional area times the original length divided by the stretch. Okay, so if that is true, then we know the force of tension, well, that is just mg. Yeah, force of tension is opposite gravity, just as if in this case the force of tension is actually equal to the spring force. Okay, so the force of tension is equal to the spring force, so we know that is just mg. Now, what's the cross-sectional area? Remember, we already talked about it. We're given a radius of 0.0031 meters, and we know the cross-sectional area is pi r squared. What is pi? 3.14. What's our radius? 0.00031 meters squared. So pi r squared. Okay, and we're going to multiply this by, what's the original length of the wire? The original length of the wire happens to be 1.2 meters long. Yeah, this is 1.2 meters. And we're going to divide that by the stretch, okay, which is 5 times 10 to the negative 3 meters. Okay, now we know mg, as we said here, mg 4 times 9.8 is actually 39.2. So if I take 39.2 and divide it by this and I multiply by that, I should get my Young's modulus to be equal to 3.1 times 10 to the 10 Newton meters squared. Okay, so this would be my Young's modulus, and that's how we calculate the Young's modulus. Now, a good question to ask is, what is the stiffness of a typical interatomic bond of the alloy? So we want to find the stiffness of one interatomic bond. Well, remember how we relate the Young's modulus to the interatomic bond. You say the Young's modulus is equal to this K sub S sub I, yeah, which that means that it's a spring stiffness of an interatomic bond divided by the distance, yeah, but divided by the distance between the two atoms. So therefore, if I want to find the spring stiffness for an interatomic bond, I'd say K sub S sub I is what I'm solving for, and that is just simply equal to y times d. So in this case, all I do is multiply my Young's modulus times d, which is the distance, the average bond length here. In this case, the average bond length between atoms is 2.5 times 10 to the negative 10 meters. Yeah, so that's my distance. So 2.5 times 10 to the negative 10. I'm not going to worry about plugging in units until the end. Okay, and so if I put this in my calculator and multiply, yeah, I get my answer to be 7.8 Newton meters. Okay, so this is a classic Young modulus problem you'll probably see on your test.